Alright, in this video we're going to be going over power series. This is our last video for today, which is geometric power series. Now, let me see if I can... Hey, my lasso tool is back and working again. That's awesome. Good to go. Okay, so to do geometric power series. Oh yes, and I turned off my video in the bottom right. I noticed it was causing some lag when I was scrolling, so hopefully when I scroll it doesn't look all fuzzy. Alright, so first off, let's just review some geometric power series. Here's basically how it looks. It's often represented as a sigma of a r to the n. A just kind of represents a constant. In the event that n is 0, this constant is the first term in the sequence. Note that if n is not 0, then the first term is not just a. That's a pretty weird idea, but basically, pretend we drew some sigma with n starting at 2. If you had some a r to the n, the first term in the sequence is a r squared, which is not just a. So just note that as long as n is 0, then a is the first term. A is the first term only because n is 0. If these are different, these must be true together. So just pay attention to those. R is the common ratio. It represents how something grows. Say I told you to start with a is 2 and r is 3. What geometric series would you write? So a is the first term. That's 2. Since r is 3, each term afterwards is multiplied by 3. So we're going to get 2, 6, 18, 54, and so on. Now, because it is a series, these are technically added together, so that would be our answer. What if a is 2 and r is negative 1/3? Then it'd be like 2. You multiply by negative 1/3, you get minus 2/3. Then you get plus 2/9, minus 2/27, and so on. If you wanted the general term, you could say it's just 2 times negative 1/3 to the n. If you wanted the general term for the one before, it'd be 2 times 3 to the n. N starts off at 0 in these because if you plug in n as 0, you get the starting value. That's kind of what we meant by the first term being what it is. Depends if you start at 0 or not. Alright, and what if a is 1 and r is x? That means we start off with a value of 1, and to get to the next term we need to multiply by some unknown x. And now you can start to kind of see an idea forming. The idea being that the first examples were all just numerical values. The only variable in the question was n. N is like the looping or iterative sigma variable. So sorry, I had to get a yawn in. I'm not used to staying up this late, old man bedtime. X to the n is what we're getting down here, and notice that we have x to the n as part of our power series. It's a power series because we have x. So our review is basically just remember geometric series look like this form, and what we studied before were geometric series as functions of n, but now we're studying geometric series where they have x's in them. Now what's interesting is that if a geometric series converges, we know what it converges to. We know that the infinite sum, S infinity, is a1 over 1 minus r. I would recommend you improve your notes. You can write this as S infinity and a1. These small improvements to your notes remind you a few things. First, a is the first term of the sequence. Sometimes people call that a1 to represent it's the first term. It can be a little deceiving because you might say, well, shouldn't it be a0? And in which case I say, sure then, make it a0. Whatever you have to do to remind yourself that a0 or a1 or a something is just the first term of the sequence. I like the s sub infinity because it just reminds me it's infinite sum, but either is fine. Remember that a geometric series converges so long as the absolute value of r is less than 1, and it diverges if it's greater than or equal to 1. That includes when it's equal, so we don't have to check endpoints like we were in the ratio test. So if you know it's geometric, there's no need to check an endpoint. It diverges at both endpoints, positive and negative. 1 for r. So what's nice is when you're given these formulas, you're just going to go backwards. We have a1 over 1 minus r. We have 1 over 1 minus x squared. It's telling us that it's centered at 0, which makes life easy. Give the first four non-zero terms and the general term. For what value does your series converge to f of x? For what values of x does it converge? So we want to match 1 over 1 minus x squared. We want to match that into a1 over 1 minus r. This one's a nice simple one. We could tell that we have a1 is 1. or A0 if you prefer that notation better, that's totally fine. We can go ahead and make these A0s. I kind of prefer it, truthfully, as well. And then we get r is equal to x squared. So that means we should get a sigma from n is 0 to infinity of x squared to the n power, which would just be the same thing as saying x to the 2n. Write the first four non-zero terms. That should be pretty simple. When we plug in 0, we get 1. When we plug in 1, we get x squared. Plug in 2, we get x to the 4, and then x to the 6. Right, the general term we already did, it's x to the 2n, and for what value of x does it converge? Well, remember that the geometric series converges so long as the absolute value of r is less than 1. In this case, r is x squared, so the absolute value of x squared is less than 1. There's no need to have an absolute value on x squared. It itself is already a positive, therefore x squared must be less than 1. Now, if x squared is less than 1, that really just means that x is less than plus or minus 1, which is kind of a goofy way of saying negative 1 is less than x is less than 1. The reason why I said that's kind of a goofy way of writing it, it's kind of more of a logical question than an algebra question. If x squared is less than 1, x surely has to be a number between negative 1 and 1, not inclusive. We don't have to check endpoints because it's geometric, so that's nice. Find a power series of this thing centered at x is 0, give the first four non-zero terms, and the general for what values does it converge. Now remember that we're kind of forced to turn this into, in green, we need to convert that into a 0 over 1 minus r. The 1 is really the flag, or the important part of the question, and paying attention to the center. Now when the center is 0, life is easy. We just want r. If we did have a center, like in this next question, when we do have a center, we're going to want it to say a0 over 1 minus r minus c. So that's kind of how we're going to do that part. But we'll get there when we do. In this one, the center is 0, which makes life simple. If we want to make the 4 into a 1, we're going to have to divide by 4. The easiest way to show that division by 4 is to factor it out. After factoring it out, we can go ahead and divide these terms together because why not? They kind of make the a naught anyway, so we might as well divide them out and get 3 over 1 plus x to the 4. This means that we have a geometric series whose a0 is 3 and r is negative x over 4. Remember that the formula has a minus in it, so whenever you see a positive here, we get a negative and vice versa. To write our sigma, we can do n is 0 to infinity of 3 negative x over 4 to the power of n. It wants the first four non-zero terms. Let's go ahead and do that. That would be 3 minus 3x over 4 plus 3x squared over 16 minus 3x to the 3 over 64. I'm getting these by just plugging in n is 0, n is 1, n is 2, and 3, and writing down the results into here. So like, hopefully that makes sense. Remember that 4 is also raised to the power of n. Alright, after reviewing some things, I think this is starting to come back to me. Basically what this part is saying is if you're trying to find the sum of a series, it might help to try to focus on the pattern. Luckily, they give us the general term. So we should start by analyzing this general term. Does this look familiar to any other series we've covered, specifically the special Maclaurin series? It took me a second to see it as well, but I thought of it as e to the x. E to the x is going to be 1 plus x over 1 factorial plus x squared over 2 factorial plus dot 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 plus x to the n over n factorial. Now compare these two things to each other and recognize there is only one difference. This is x equals 3. If x is equal to 3, these are equivalent, which means that the answer of this is simply just e cubed, because we're replacing this with x equals 3 and recognizing that this sum is just the expansion of e to the x, where x has been evaluated for 3. All right, for the next one, we're going to look at just the general term to start us off. This is looking very odd, specifically like odd as in the opposite of even, not odd as in strange. I'm noticing the alternating component in the numerator and the 2n plus 1 factorial and the 2n plus 1 exponent. This makes me feel like this is probably sine of x. The sine of x can be represented by a bunch of terms that we don't really care about at the moment, but really the sigma from n is 0 to infinity of negative 1 to the n, x to the 2n plus 1 all over 2n plus 1 factorial. Now, if you compare the two things we have, you're going to notice that they're exactly the same, except x has been plugged in for 2, which means that we go over here, we say, oh, x must be 2, therefore this is the sine of 2. The sine of 2 is equal to this giant ugly answer, which is therefore our answer to find the sum of this. So you see, we're not actually finding the sum by directly computing it. We're finding the sum by writing out the expansion and finding what looks similar to it. Same idea down here, except this one I think is very straightforward. We have this here, which is looking like r to the n. This means r is negative 2/3. To find the first term in a sequence, you can just look at it. A is equal to 1. Therefore, the infinite sum is equal to a11 minus r, which in this case would be 1 over 1 minus negative 2/3, which is 1 over 5/3, or 3/5 as it's commonly known as. All right, for our next part, it's basically saying, what happens if we can't figure it out? What happens if it's not just this easy? The answer is sometimes it's off by an integral or derivative, hence why I guess we are all in calculus to take derivatives and integrals. So what this one's saying up here is that if we have some function, the derivative and antiderivative look like this, which is very simple. The derivative of this thing, you just bring the n down, you bring the n down here, and then you subtract 1. That's how you get the n minus 1 and n. And instead of taking a derivative, if one was to take an integral, you would add 1 and then divide by the new value. That's what this is giving you over here. Remember that the radius of convergence is the same. However, the interval of convergence, you have to check the endpoints. If we're using geometric ideas, we know we don't have to check the endpoint. It diverges. However, in these ones, it might not always be that way. So we'll have to see. The function f is defined by 1 over 1 minus x. Write the Maclaurin series. Give the first 4 non-zero terms general term. And for what values does it converge? This is going to be our most straightforward case of a0 over 1 minus r is the infinite sum of a geometric. Meaning, all we have to do is identify those three. A0 is 1, r is x. Therefore, we have the sigma from 0 to infinity of x to the n. This is given by the first terms of these, and that should be good to go for that. For what value does it converge? Well, we know for convergence, the absolute value of r must be less than 1. That's the absolute value of x less than 1. That means it converges from negative 1 to 1. We do not have to check endpoints because it's geometric. So because it's geometric, endpoints not needed. X equals negative 1 diverges. X equals 1 diverges. That is how geometric works. So we're good to go. Use your answer to part A to find the Maclaurin series for f prime of x. Give the first 4 non-zero and general terms. So f prime of x would be the derivative of this sigma. We have our sigma, which is n is 0 to infinity. We're going to go ahead and take a derivative. When we go and take a derivative, we're going to get n x to the n minus 1. And we might want to test this last point here, the beginning point of n is 0. I believe actually it is n is equal to 1. Although if you did plug in 0, you'd be okay because it would have been 0 times x to the 0 minus 1, which would have worked out. It's a little more natural instead to just get rid of the first term. Recognizing the derivative of 1 is 0, meaning that we want to start counting at n is 1. And remember, this guy started at n is 0. Write out the first 4 non-zero terms. Sure, no problem. That's going to be 1 times x to the 0, which is 1, plus the derivative of this one, or if you just want to plug 2 in, that's going to be 2x, plus 3x squared, plus 4x cubed. General term is already here. And then for what values does it converge? It didn't ask, but it would be identical. We don't have to check endpoints because it's geometric again. One thing I do want to note here, however, is that we can think about what would f prime of x actually have been. If f of x is equal to 1 over 1 minus x, that's the same as 1 minus x to the negative first. That means that f prime of x is the derivative of it. F prime of x would be negative 1, 1 minus x to the negative 2 times negative 1. The negative 1 here coming from power rule, the negative 1 on the right coming from the chain rule. Simplifying those, we will get a value of 1 over 1 minus x quantity squared. That means that this series here is equal to this series here. Or rather, the series on the left is equal to the function on the right. So this is actually just equal to 1 over 1 minus x quantity squared. Use your answer to B to find the sum of this infinite series. So now we're just going to compare this general term here to this one here and try to find a difference. The only difference being that now x is equal to 1/3. The reason why I know x is equal to 1/3 is just because it's in the denominator. So we just want x is equal to 1/3. And then we could represent it with this sigma. So what that means is we really want f prime of 1/3. F prime of 1/3 would just be 1 over 1 minus 1/3 squared. And that is going to be 1 over 2/3 squared, 1 over 4/9, which is 9/4. Now I went pretty quickly through that. I can explain my logic. First thing was recognizing where this came from and that these are related if we allow x here to be 1/3. X here had to be 1/3. Once we recognize that x is 1/3, that really just means that the whole thing, is really just f prime, which is really just this thing, at 1/3. So once you recognize that x is 1/3 here, that also means x is 1/3 here, and x is 1/3 here, and then you just plug and chug. All right, our last page of notes today. Use the integral A to find the integral. Use your answer part A to find the integral of the Maclaurin series. Find the first four non-zero in general. We can go back up to A real quick. It was just this one. Yeah, just x to the n is 0 to infinity. This represented the sigma of 1 over 1 minus x. Now, if we took the integral of all of this and we take the integral of all of this, we're going to get the integral of 1 over 1 minus x, which we're going to figure out in just a minute. And the integral of x to the n is going to be x to the n plus 1 over n plus 1. And we have our sigma. We'd want to verify that n starts at 0 or not 0. I'm just going to write 0 for now. We'll double check in a second. If we did plug in 0, we'd get x. If we plugged in 1, we'd get plus x squared over 2, then plus x squared over 3, and plus x to the 4 over 4. We don't really have to write the general term because I already wrote a sigma, meaning this is the general term. And now we can verify that we're correct. We know that in blue, we had the function 1 plus x squared plus x cubed plus dot 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 x to the n. Integrating those terms should directly lead you to here. The integral of 1, the integral of x, the integral of x squared. These all look great to me. I don't believe we have to change n as a result of them matching up just fine. Now what's interesting is we can do some work on the left side. The integral of 1 minus x is equal to the negative ln absolute value of 1 minus x, which should be the same thing as the ln of 1 over 1 minus x, surprisingly. Because you can bring the negative in, and then the negative can be an exponent. That feels quite weird, but I think that's correct. I'm going to hit pause on my video and double check. Alright, that one seems perfectly good and normal. I think it was just a funny coincidence, if you would, to why these look the same if you simplified. But what we've learned is that this value here is equal to x plus x squared over 2 plus x cubed over 3 plus dot dot dot. And it says use this answer to find the sum of this infinite series. So we're using the representation that fits us best. Here is what we are given. And we want to try to find a way to match that up to something we have. Once again, I think this is probably the easiest representation here. So seeing that the n plus 1 is the n plus 1, this x is in the numerator, whereas this x is in the denominator, this 3 is in the denominator. I once again think we just get x equals a third. So that means we can use x equals a third everywhere. We said that this is the integral of 1 over 1 minus x, and we said that gets to here. So my theory is this is the ln of 1 over 1 minus a third, which is just the ln of 1 over 2 thirds, which is the same as the ln of 3 over 2. So your trick here is really just like you stare at the two things and try to figure out what x has to be. And this allows you to sum some quite weird formulas. Alright, hopefully these videos helped. Have a good rest of your day.